We now have a handful of ways to prove whether a series will converge or not. Let's take a look at what we have so far. So we have a geometric series, which if the series looks like this, a times r to the n, it's geometric. And if r, the absolute value of r, that is less than 1, then this will converge. And we know what it'll converge to. It'll converge to 1, or a, over 1 minus r. Now, remember that these tests here prove to us whether they converge or diverge, but it doesn't necessarily give us a value that it converges to. The geometric series is special in that case. Next, we have the nth term test. And if we have a series and the limit of the values of a sub n is not 0, then this tells us that the series diverges. Now, we don't know if it converges. It doesn't tell us anything about convergence, but the nth term test will tell us about divergence. We have the telescoping series test. Well, if every other term is canceling out, then we will know what it is telescoping, and we can find that limit because it's just the first and the last. Or really the first term minus the limit of the last term. Okay? So next we have our integral test. So if we have a series, and this is a little typo, it doesn't have to look like this. Some series a sub n, all right, and that series is equivalent to f of x, all right. So then we can take the integral of this f of x from 1 to infinity, and if they both diverge or they will both converge. So if the integral converges, then the series converges. If the integral diverges, then the series diverges. All right. The p-series test. All right, that's our last one so far. All right, that means we have a special form again. That special form is that we can write it as 1 over p to the n. And if n is greater than 0, this will converge. So now we want to look at what happens when it doesn't perfectly fit one of these, but it's close. So let's consider these two series. We have the sum from 1 to infinity of 1 over 2 plus n squared and 1 over n squared. So let's graph these sequences together. We'll use x instead of n and see what they look like. So here they are. Now they don't look very much alike towards the middle, but remember, we're just talking about when x is from 1 to infinity. All right, so let's go here. All right, and if we can zoom in, let's see if this will let us zoom in. Okay, so they're pretty much alike pretty quickly, all right? They're different. There you go. You can see them there. Okay, they're different, and they're obviously different as we get over here towards 1. So they start out, they're kind of different. Now we're at x of 2.83, and they pretty quickly get really close, all right? But notice this. Which one's always on top? It looks like the blue one's always on top, all right? The blue one's always a little bit higher than the red one, okay? So what we want to do is we want to say, well, if we know that the blue one's always on top of the red one, and maybe we can't handle the red one, but we can handle the blue one, then if the blue one closes in on a certain sum, then the red one will also close in on a certain summation. All right? So if that blue one converges, we know the red one will. All right? And we do know that the blue one does. But let's hold off on that for a minute. So let's put this all together. So how do the sequences compare to each other when n is greater than 0 there? Well, we know that 1 over n squared, so that's the b sub n, is always greater than a sub n. All right, so the values of the sequence. All right, so which series can we easily determine the convergence of using tests that we've learned? Well, this second one. All right, that's easy to figure out. So the sum of n equals 1 to infinity of 1 over n squared converges by which test, you know? Well, that's the p-series test. So it's a p-series because it's in the form 1 over n to the p, and p is greater than 1. All right? So what does this tell us about the other series? Well, since b sub n is always less, or a sub n, sorry, is always less than b sub n, so this one is always less than this, okay, then, so we know that, let's write this out, 1 over 2 plus n squared is always less than n equals 1 infinity. Okay, so since this one is converging, it's going to 0 eventually, all right, or it's going to sum total, I should say. This one has to also. One way I like to picture this is kind of like a ceiling effect. So this is the ceiling, and kind of like our graph we just saw there. So we have one graph that's the ceiling kind of closing in on this other graph that's underneath it. And if this black series here, okay, the graph represents the series or the terms of the series, okay, as we know this one converges, it kind of closes in on this one. This one must also converge also to something. Okay? Well, let's look at another two, and we're gonna change these a little bit here. Let's change this one here to ln over 1 plus n. And we're going to change this to 1 plus n on the bottom. And I'm going to change this to 1. All right. I know that kind of changes the whole problem, but this will show us more what we need to see. I'm going to change the rest of them down here. Let's graph these two functions on Desmos here. So we have 1 over 1 plus n, or we're going to do an x here. So we have 1 divided by 1 plus x. And we'll zoom that. There it is. And we have the natural log. Let's find our natural log here. Somewhere, where'd you go? Probably passed it up 3 times. There it is. Natural log of x divided by 1 plus x. All right. So there we have it. Okay, so now we're looking at these. Now notice at 1 here, the red one, 1 over 1 plus x is greater. But then and at 2, it's greater. And then from 3 and beyond, notice that this function, the blue function, is always greater. Okay? So we call that term by term. So we can analyze that term by term. So when we graph them together, all right, we got we see the fact that ln of n, or 1 plus n, is greater than 1 over 1 plus n, and that is for n greater than 3. Now we saw that on the graph, and we could also make a quick list for ourselves. N is 1, 2, 3, 4, and we can check that out if we have 1 over 1 plus n and ln of n over 1 plus n. So what really matters is the top, right? But anyways, this is 1/2, this is 1/3, this is 1/4, this is 1/5. And the ln of 1, ln of 2, ln of 3, and ln of 4. Well, what is this? Well, you can compute these, or E is about 2.718. So what power do you put on 2.7 to get 3? Well, it's bigger than 1. So at this point, from 3 on, the natural log of 3 is greater than 1. So that's what's going on there, right? So we can analyze that, and we can convince ourselves that that is true. All right. So now we can use the series test that we know to figure out the convergence or divergence of 1 over 1 plus n. We'll check this out. 1 over 1 plus n, the sum there is 1/2 plus 1/3 plus 1/4 plus 1/5, so on and so forth. And we need to compare this to a sequence we know, and that is the harmonic sequence, which is 1 over 1 plus 1 over 2 plus 1 over 3. You get the idea. All right. And notice that these are the same, all of these and all of this. All right. So we could say that this new one, n equals 1 to infinity of 1 over 1 plus n, is really just 1, or let's say this blue sum, n equals 1 to infinity of 1 over n minus 1. And so since this blue thing we know goes to diverges, this whole thing must diverge. All right, and you might have just kind of assumed that because this is pretty much the same as 1 over n at infinity. And so this one diverges. Okay. So what does that mean since the natural log of n over 1 over n is greater? Well, what that tells us is that's going to diverge also. I like to think of this as a floor effect. So we're going to raise the floor, all right? So we have this function, let's see. We've got this function 1 over 1 plus x, all right? And that's going to look something like this. And we know that that's always below, at least after 3, this other function, okay? So this red one doesn't converge, it diverges. I'm sorry, this blue one we know diverges. Okay, the blue diverges. And the red is always bigger than the blue. So since the red is bigger than the blue, well, the sum of the terms of the red series is never going to converge because it's always more than what the blue is adding on. So the blue keeps adding on, adding on, adding on, and the red's adding on, adding on, and the red's never going to dip below the blue. So the floor holds this up. This divergent floor will prevent the red function or red series from converging. So the red one must diverge also. So this is what we call the direct comparison test. All right. Direct comparison test says this: if we have two sequences or terms in the sequence, a sub n and b sub n is always greater than a sub n. We call this term by term. So each term in b is bigger than its corresponding term in a. So if that's true, and we know, so if we know that B converges, so B, which is the bigger one, B for bigger. If the bigger one is closing in, is converging, then we know that the smaller one, A sub n, also converges because it's going to close in the ceiling. All right. On the other hand, if A sub n, the smaller one, diverges, so if this one blows up, in other words, it never gets down to a total there, all right, well then B sub n, the bigger one, will also diverge. Okay, so this is, right here, is dropping the ceiling. Okay, the ceiling is closing in. The bigger function is closing in. This is raising the floor. So if the smaller one is getting bigger, then the bigger one must get bigger also, or it just doesn't converge. Okay, it's not closing fast enough. So, all right. So that's the idea. If B sub n is converging, that ceiling is closing in. A sub n must converge. Okay, we're raising the floor. If A sub n diverges, it'll kind of raise the floor on B sub n, and B sub n can never diverge. All right. So the challenge here is finding a similar sequence that will perform one of these effects. Okay. Now, got to watch out here. Okay, it doesn't do us any good if we know that A sub n converges. It doesn't tell us anything about B sub n. Okay, so if we've got two functions and we've got this smaller one here and this larger one here, if we know that this one converges, well, that doesn't necessarily mean that the bigger one's going to converge. This could stay too big until it never converges. All right, vice versa. Okay, let's see here. Okay, if we know that, we've got this one up here, and if we know this top one, let's see, if this one diverges, in other words, it never closes in fast enough to get it to be convergent, that doesn't tell us anything about this question mark. Okay? Okay. So if the ceiling never closes in, we don't know anything. If the floor never raises, we don't know anything. So got to watch out for that. All right. Next, we'll look at the limit comparison test.